Thank you. Cześć Polska, jeszcze masz. Oh, thank you. Thank you. That was my talk in Polish, so I'll spend the next 30 minutes translating it in English. Please bear with me. So recently I got a chance to write a thread profiler for work, and I was amazed by how ridiculously easy it was to do this in Python. So I'm just going to share the things that I found during the creation of the thread profiler, and hopefully it'll help someone write your own thread profiler because you're wide awake at 3 a.m. because you're kind of jet lagged and you're wondering what to do. So let's start. My name is Amjith, and I go by Amjith R on Twitter. You're welcome to follow me, although I rarely tweet, so I don't see any point in doing that. I love Python, so I really do. It's my favorite language. I like it more than my native tongue, which, by the way, is not English. So if you find me, saying some complicated word, it's not because I have a rich vocabulary, because I'm probably mispronouncing something. So there's that to look forward to. I work for a company called New Relic. How many of you here know what New Relic does? Oh, that's awesome. Thank you. Nice. So we're in the space called application performance management, which is just fancy talk for you pay us money and we let you install our software and we show you pretty graphs. And we also email you and stuff when your server is melting. So that's pretty much what we do at New Relic. Enough with the background. Let's get started with the actual talk. Let's begin by answering a very simple question: what is profiling? Many of you might already know this, but it's just the action of just measuring the performance of your script. And how can we do this in Python? Many of you know this famous quote, or it's like an unofficial motto of Python, which is batteries included, which comes from the standard module has everything that you need. If you're wondering how to fly, then all you have to do is just import anti-gravity and you're good to go. True to its word, Python standard library does come with a C profile module, and it's very simple to use. Let's say you have a script that you usually run by calling python lcm.py. All you have to do now to profile that is python-m cprofile lcm.py. And suddenly you get a bunch of information about your script, which gives you how long it took to run, how many function calls were made during that execution, and what are the different function calls, and how many times they were called, what is the time it took to run each one of them, and a bunch of different information like that. And you can use this information very well to sort of optimize your code and make it run a little bit faster. So cprofile is fantastic. But there is a slight problem. Its UI is CLI, which I love, but in this case it has an issue because the last time I tried running it on a Django application, it produced an output which was like 5,000 lines long, and my scroll back wasn't long enough to go back all the way to the top to get the screenshot. It was that big, and so if you are running this on a really large project, you might sometimes find yourself with a ton of data that is kind of overwhelming. In that case, you have a better option. You can use a GUI called Run Snake Run, which is cleverly named, I think. And this is a WX Python project that gives you a GUI, and you basically write your profile into a file, and you open it with Run Snake Run, and it produces gorgeous square maps. Well, it produces square maps. Let me just show you a screenshot of that, because that's not just a screenshot, but the actual application. So this is the actual application for that particular one, and here you get an option to sort by the number of calls that are made, by alphabetical order if you want to just sort them, or if you just want to drill down into this specific one, you double-click, and then you can just jump all the way down and keep double-clicking, and you can drill down and find out exactly how which functions are taking the longest time and what's its call graph and that sort of thing. And so clearly, the bigger the box, the more time is spent in that particular function. So that's how that GUI works. So that actually gets us pretty close to what we need and how to optimize our code. But there is one small catch. If we run our code without the profiler turned on, this is one of the examples where it took about 5 seconds to run my code. With the profiler on, it took about 10 seconds to run. It's 100% overhead. I mean, you might be thinking, it's not that bad. I mean, it's not terrible. Well, Picard kind of disagrees because he wants to run it in production. If you're wondering, like, who the hell runs Profiler in production, only the most successful company in the world. You might think that when you run a Google search and they show you that, we found 3 million pages and they say we found this in 0.16 seconds, you might be thinking that Google is just boasting, which they are, kind of. But they're also a person there sitting and wondering, if that number goes above a certain threshold, there's an army of engineers who are going to, work their butts off to bring that number back down, or throw a ton of hardware to bring it back down to a minimum level again. So you constantly have to be profiling your own results in order to find out, when things are going wrong and when how to find them and fix them quickly. So running Profiler in production is a worthy cause, and we should actually be, striving for that. So we kind of established that cProfile is too slow to run in production, and if we're not running in production, that makes Picard a sad panda. So what can we do? We can take a different approach, which is, most parents will agree with me here. You could do targeted profiling, which is kind of like, picking your favorite kid and then sending her to college. Sorry, that's a terrible joke. Anyway, you pick your critical functions that you want to monitor because this is business critical, and then you do some sort of a hybrid profiling. The reason I call this hybrid profiling is because that's kind of what we do at New Relic. I'm literally giving away the secret sauce here. What we do is we target very specific web frameworks like Django, Bottle, or Flask, or a ton of other ones that I haven't listed here. And these web frameworks have a definite recipe in which they work, which is basically you go to a URL and then the control gets transferred into a view handler. It basically gets routed to a view handler, and in the view handler you basically talk to your models, which are your databases, and you generate the information and then you present that information to the user via templates. The critical functions in these web frameworks are the view handlers, the model layer, and the template layer. So if you can find a way to time those things automatically, then those cover pretty much 90% of your use case. So this is a screenshot from New Relic's transaction trace, a very specific web request. When that happens, this is how the control gets transferred, and we just time only the top level functions. We don't time every single function that gets called from your view handler. We only time the view handler itself. But I mean, if you're making calls to SQL and so on, the reason I call this hybrid profiling was because in addition to just timing them, we also capture the arguments that are passing into the function, so we can reconstruct the data of what was the request that caused this slow request to happen. So for example, I expanded out one of the SQL queries so we can show you the SQL statement that got captured, which took about 60% of your response time. So this is like a perfect example, but it's not always sunshine and ponies. Because if you're only picking critical functions, you're going to obviously find some holes, because in case you write your view handler which calls 50 different sub-functions that are doing very custom work, we're going to club everything into application code. That's code word for we don't know what the hell you're doing. So this, again, it kind of falls short of a couple of things. I know you guys are getting annoyed, this talks about threat profiler. When are you going to get to it? I'm almost there. So I'm going to introduce threat profilers, or as I call it, statistical threat profilers, using a simple analogy. Your statistical threat profiler is like an overly attached girlfriend or a boyfriend. Let me explain. An overly attached behavior is categorized into three sections: interrupt, inquire, and collate. Imagine getting a phone call every hour, or a text message, and asking where you are, or who are you spending time with, or who are the people you're hanging out with. And if somebody were to take notes very diligently for about a month or about a week, they can pretty accurately tell how you spend your Mondays and Tuesdays, who your friends are, and what times you do what are the different things. You might think this is overly attached behavior, but this is exactly what a statistical profiler does. Let me put it in a different view, with a very professional rendition. What I'm showing here is a single thread that's running a very long function. If you interrupt it at very regular intervals and then you ask that thread what it is doing at a given time, you can pretty easily tell which function is the one that's occupying the CPU at that given time. So it kind of gives you a representation of where your time is spent, which function is occupying the CPU at any given time. So it does not give you exactly how long it took to run a function. It basically just tells you how frequently a function might be called and how frequently a function is occupying the CPU time. If it is a very short function, but it gets called millions of times, again, the chances of that function appearing whenever you interrupt your process is going to be very high. And that is the function of interest that you want to be optimizing. So that's the basic idea behind a statistical thread profiler. If we are going to translate this into Python, how can we do this? OK, so let's look at each category in detail. Interrupting. We could be interrupting a running process in two ways. One is using Unix signals, or you could be using a background thread. If you're using Unix signals, the way to interrupt this is, in Python, it's just 3 lines of code or 4 lines of code. You import the signal module, and then you pick a specific Unix signal that you want to use. In this case, I'm using iTimer virtual. And you're basically setting yourself an alarm, and then when that signal is sent to the main function, you basically attach a handler function. So anytime that signal reaches your process, this handler function will be run. And that's where some work is going to be done. And then you set yourself the alarm for 100 milliseconds, and it's going to repeat every 100 milliseconds. And so it's like happening every 100 milliseconds. So this is one way of doing this. Obviously, the pros is it's very accurate because it's a Unix timer that the Unix process is going to be interrupting, or the kernel is going to be interrupting your process. But the obvious con is, or it could still be considered a pro, which is it's only on Unix systems. It does not work on Windows. And if you're using Python in an embedded environment like mod WSGI, then mod WSGI is going to ignore your signal. Again, C extensions cannot be interrupted unless you write your C extension to be well behaved. It cannot be interrupted. The other method is using threads. If you're using threads, again, it's 3 lines of code, which is you import the threading module, and then you say, what is the handler function that has to run in a background thread? You start the thread, and then in the handler function, you basically sleep for 100 milliseconds. So you're basically saying, this thread will sleep 100 milliseconds, or it'll wake up every 100 milliseconds and do some very specific task, and then go back to sleep, and then wake up in the next 100 milliseconds. This is like an infinite loop that's running and waking up every 100 milliseconds. So that's actually very simple. So that's how we interrupt. Now that, obviously the pros are it is cross-platform. Threads can work in Windows or Unix, and mod WSGI will honor background threads that are running in your system. The cons are if your main function that you're running is very CPU intensive, the chances of a background thread waking up every 100 milliseconds and grabbing the GIL is not very high. Especially if you're in a multi-core system, your CPU-intensive task is not going to give up the GIL, or it'll give up the GIL, but before the background thread actually grabs the GIL, the main thread will capture back again, and then it'll continue running. If you want to get more details, you may want to look at David Beasley's talk on how the GIL works in Python. It's a fantastic talk. But anyway, so if you're trying to use statistical thread profiler on NumPy, SciPy, or something like that, then you should probably go with signals, not with background threads. Again, even if you're using threads, you cannot interrupt C extensions. So they're like the gods of the Python world. So now that you've found a way to annoy the hell out of your main function, what are you going to do every 100 milliseconds when it wakes up? Well, the equivalent of asking what you're doing or who are you hanging out with in programming terms is basically getting the stack trace of that specific thread that you've just interrupted. And getting a stack trace might sound complicated. Again, Python is a very easy language. And it's basically just 2 lines of code. Here you do import sys, and then you say sys._current_frames. And the underscore part is very important. This is a private method. We're not supposed to be using this. It's not like a public API that's never going to change, but it's there. We're going to use it. I mean, if it changes, oh well. So what this gives is it gives us a dictionary where the key is the thread ID and the value is a frame object. The frame object is the one that holds the information about the function that's actually running. So let's dive into the frame object. The frame object is like a linked list where each node represents a function in that stack trace. And that is a object which has the function name, the file name, the line number, a bunch of arguments and globals, locals, and a bunch of different information. The one that we are going to be interested in is the top three, the function name, the file name, and the line number. I'm going to get into that in just a second. How do we extract this out of the frame object? We can either do this manually by using a while loop or a for loop, or there's another built-in module that extracts this information for us. You do traceback module, and then you do traceback.extract frame, and provided the frame object's root frame, and then it gives you a list of tuples where each tuple has the file name, the line number, the function name, and the actual line which was actually executing at that given time when it was interrupted. So this is actually very nice. This gives you a list that you could just use right away. So how are we going to, so now that we have collected all the information, how are we going to represent this? So how are we going to build a sensible information call tree or whatever it is that we're going to build? Let's take a very simple approach. This attempt number one is going to use default dictionaries in Python. What we're going to do is uniquely identify a function. This is very simple. We already have this information, which is the way we identify this is a function name, file name, and the line number, and form a tuple out of that, and build a dictionary. Use that tuple as the key, and the value is going to be an integer. Anytime that key is present, you just increment that value. And at the end of the execution of your script, you get a dictionary whose keys are going to be the function names and the values are the call counts. So this immediately gives you it identifies which is the most called function, and it's extremely simple to implement. You could just use it with a print statement to get the list of functions and its call counts. But obviously, it's just a bunch of nodes without any context. Meaning, in this particular one, even though function C was called 5 times, what was the parent function that called function C? I mean, you don't get that information, and which is very important because you want to know in what context was a function called in order to optimize that function for that specific scenario. So let's make a little bit of a complicated approach here, which is attempt number 2, where we're going to try and build a call tree out of this. Now, the left side is going to be the stack traces, and the right side is going to be the call trees. First time snap, when we first interrupt, let's say that I get a stack trace which has function A calling B calling C. The call tree right now is nothing. Let's step through each of these nodes, and then we'll build the call tree as we go. So function A, we're seeing it for the first time, and so we create a node and put a call count of 1 to it. Function B, we actually make function B as a child node to function A, and then function C, we do the same thing. The next time snapshot, we already have a existing call tree. I get a new stack trace now. I see function A again, and so I increment function A. I don't add a new node. I just increment that existing node. Function B, again, increment the existing node. Now function D is new. So what I do is I make a child node out of that, and now you have a call tree. This is another example of function A and calling function D. So function A is already there. You increment that. Now function D, even though it's present in the call tree, we're not going to go through and increment it because the parent function for this was function A. So we're going to move and create a new child node. So this is preserving the context, under what context was function D called, so that we can kind of optimize it for that specific code path. So that's the call tree method. You could either build this. The tough part with this is the visualization, because these call trees, they're dictionaries. You can either use pretty print and print them out into std out, or you can use one of the existing tools that actually already does this. If you just want to use one of the off-the-shelf tools, there are 3 tools that are actually already available. One is statprof, which is in the Python package index, which uses signals. And it has a command line interface where it prints out every information that it captures and analyzes. But we already saw some limitations with the command line, so I'm going to skip over this one. Plop, this is a module that was created by Dropbox, and it was open source. And they also use Unix signals, but the visualization that they use is using D3.js. So they actually build call graphs out of this. And here's a screenshot of the UI. Again, I'm going to show you how this looks like. So this is the UI. And the first time I actually used this, I was just playing around with this for like 5 minutes before I started actually looking into what it actually does. But anyway, so that was kind of cool. And the size of the bubble actually shows you which that particular function took the longest to run. So the size of the bubble is proportional to how frequently it was called. So that's the representation that's used there. But it was kind of cluttered, but the information is still there for us to take a look at. So New Relic, I mean, I mentioned that I had to write a thread profiler. I mean, so obviously we released that, and we decided to go with background threads because we had to support all the web servers, and mod.wsgi is one of the ones that we absolutely have to support. So threads, and then we have our own GUI that we just feed the information into, and this is how it looks like. Again, and this is basically just giving you the call tree where you have the whiskey layer calling into the view handler, and a bunch of different tag methods, and actual Django framework code is also shown in that call tree. And you'll notice on the left side we have ways to identify whether a thread is serving a web request or whether it is trying to do a background task. So we can kind of bucket them into different categories, and so you can choose to see only the background tasks, for example, and then see only the call tree for that versus web requests. And that was like a nice addition to that. So that kind of gives you an idea of how to write a thread profiler if you decide to do it yourself. And it's actually very cool because it's very low overhead. All the testing that we've done shows it's under like 3% overhead if you actually run it all the time. It's very low overhead. It works on CPython, and it also works on PyPy, I tested, but it does not work on Jython. So if you're using Jython, then you're out of luck because the sys.current frames is not implemented. And again, if you are trying to introspect green threads using greenlets or eventlets, again, you're out of luck because sys.current threads does not give you the stack trace for the green threads. But there are other methods that you could use, but it has its own complications. So I'm not going to go into that right now, but we can talk about that later. If you still have questions, you can come talk to me. So that's how we get to run the profiler in production, which is very exciting. But for the grand finale, so this is something that we recently released at New Relic. So what we thought was, we have the deterministic profiler where we have the transaction traces which show you exactly how long a function took to run, but obviously it has holes because we're not instrumenting everything. And then we have the statistical profiler, which does not give you how long a function took to run, but it gives you a representation of how frequently a function got called. So we decided to combine those two together, and we called it X-ray sessions, where you choose a specific web transaction, like picking your favorite child, and then you decide to run your X-ray session on it, and it captures up to the first 100 web requests that happens. It captures deterministic information about that. And it also runs the thread profiler only for that web request, in that context only. So any holes you find in the transaction trace, you can come to the thread profiler to take a look at which was the worst offending function in that specific web request. And again, so you combine those together, and you get histograms, response times, and throughput, and all of that stuff. So that's the X-ray sessions that we just released. Thank you very much. That's the end of my talk.